Hello, my name is Peng. In this topic, I want to introduce my personal project, the Distributed NVMe. It is a distributed block storage system. So it's a kind of software-defined storage. It's a cluster typically run on x84 or ARM servers. It exports the virtual block device over the standard NVMe off interface. So there is no additional driver required on the host. And we could also use RDMA to improve the performance. According to my test, the performance looks good. We can have more than for a single virtual block device. It could have more than 2 million IOPS. It's for 4 kilobytes random write I/O. And when I test it, I try to keep the average latency less than 1 milliseconds. It's just run on a general x86 server, and when I tested it, it used the TCP NVMe off. No RDMA, no hardware offload. So it's possible to get a higher performance if we use RDMA. And it uses the NVMe multipath for HA. The NVMe protocol has defined the multipath, so it has multiple virtual controllers connect to a host. And when I test the IOPS, one thing I try to highlight is the internally, it just uses the official Linux kernel as the data plan code. So there is no magic on the data plan code. I just use in Linux kernel, it supports NVMe host, NVMe target, and it has a device mapper module, which could create logic devices, and it has some functions like read for redundancy or encryption or synchronization snapshot. I just use for the data plan, I just use the official Linux kernel. The kernel worked as a Lego piece. I can use the different Lego pieces to combine them to a whole cluster. So in my project, I just create a control plan to control these components. And it has some enterprise level features like a read for redundancy and sync provision. And finally, it is open source. Here I want to show how I built this system on top of the Linux kernel functions. We can start from the naive, simplest architecture, and then try to add more features to this system, or let it become scalable and flexible and no single point failure system. First, let's see, this is the simplest architecture. All components are in the same server. We have 2 disks. We can aggregate them to a logical device by device mapper. Such as, for example, we can create read, create sync provision, or something else. Obviously, it has some. It's not suitable for distributed environment or for some workload like a Docker or container. For example, when you run a container, a container scheduler may move the container from one host to another host. Then if we just use the local disk, the disk data cannot be, it's hard to move the disk data to the new host. So we could improve it a little bit. We split the architecture to host and target server. We create the disk. We create the a disk on the target server and export it over the NVMe protocol to the host. In this case, even we can change. Let the target server export to different hosts. For example, a virtual machine or a container is moved to a new host. We can export the same disk to the new host. It is better than the previous one, but we can continue to improve. We can still continue to improve it. Here we split the target server to two layers. One is controller node. Another is the disk node. So in this case, the disk node connects to the physical disk and export the disk to the controller node. The controller node works as a controller, an NVMe subsystem controller. The host connects to a controller, and the controller writes data to the real disk on the disk nodes. So in this case, it is better than the previous one. For example, when one disk failed, we could find another disk in any other location. Just export the disk to the controller node or the NVMe protocol. So it is more flexible. And we are easy to extend our capacity. We can just add more servers. Right now, assuming we have a large cluster, we have more and more users. We need more and more disks. We just add more disk nodes and controller nodes separately. And each controller node can access each disk node. When a user wants to create a volume, we just allocate some controller node and some disk node and build a virtual NVMe subsystem on these nodes and export it to the host. The controller node worked as a controller. We will build most of our, I should say, enterprise level features on the controller node. For example, we create a separation and read and maybe encryption and all others on the controller node. For the disk node, we just create a logic device on a part of the physical disk, export it to the controller node. And then here is a view of multiple users. We may have multiple virtual NVMe subsystems. Each virtual NVMe disk is distributed to different controller nodes and disk nodes, and they can be exported to the different hosts. until this stage, I think we arrive at a milestone. Until now, it is already a distributed system. So for each virtual disk, it is distributed to the different servers. Its data is distributed to different disk nodes, and its controller may on any of the controller nodes. Although it still has lots of problems, but anyway, on this stage, it is distributed. And first, obviously problem is the controller is a single point of failure. For disk, we can have a read for redundancy. So for one disk, if one disk node failed, and assume we create a read 1 or read 5, we can still read write from other disks. But if a controller node fails, all the controller on this controller node will not work. A straightforward way is adding a standby controller. So for a single virtual disk, we have an active controller and a standby controller. The host connect to both of the controller or the NVMe multipath. So the multipath is defined in NVMe protocol, and it has the NVMe spike defines the different states of the multipath. One path, the green path, could be the optimized path. It means it's the preferred path. So the red line, I will set it to the inaccessible state. So if the host follows the NVMe protocol, it will know it will always send I/O to the optimized path and do not send any I/O to the inaccessible path until we run something like failover. We can have a control plan code. If the controller node, node failed, we will promote the standby controller to the active controller and change its status to optimized. Then the host will know it and send I/O to the standby controller. In this way, we already have no single point of failures. So we can have multiple, for the controller, we can have multiple controllers on different servers. For disks, we can use different read levels for data redundancy, and the data are also on the different disk node servers. But a problem is the controller node will be the bottleneck of the performance. For example, you create a read 1. The host sends one request to the active controller. The active controller receive one request and dispatch two same requests to the disk nodes. So for one request from the host, there are 3 requests on the active controller. If the host sends lots of requests, for example, 200 million IOPS, then the active controller should handle 6 million IOPS. It's a big challenge for a single controller node. And this is a read 1 case. For read 5, read 6, or erasure code, the scenarios will be worse because the controller should also read data from for write request. The controller node should also read data from the disk and then calculate and run some calculation and then write the result back to all the disks. So we try to find a way to remove the bottleneck. Here is a straightforward way. We can add a dispatcher layer, create a read zero on the dispatcher layer. In this case, we have multiple active controllers. Each active controller on parts of the virtual disk, and we can create a read zero on all these active controllers. So there are multiple read zero, but they are exactly the same thing. We just create them on different dispatcher node, and we export all this read zero to the host. From the host view, it just connect to multiple active controllers, and it can dispatch the request across all these paths, and the request are distributed to the different servers. So the dispatcher node works as like a load balancer. One thing to notice, although NVMe spec defines the multipath and could have multiple optimized passes, but the NVMe spec doesn't define how to use these optimized passes. For the host, it could just select a single path, send all traffic to that path. It could also send the traffic across all of these paths, or maybe only a subset of these paths. That depends on the host. So in this architecture, we add an additional requirement for the host. If we want it to work, the host should send traffic to all these active controllers or to all these optimized paths in round robin. Anyway, until now, the Linux kernel supports this way. So if the host is a Linux system, we can configure the kernel to send the traffic in round robin to all these paths. So it works. And then we can optimize this architecture a little bit. We don't really need a separate dispatcher node. We can combine the dispatcher node and the controller node together. We just put the dispatcher layer and the controller layer to the same layer. Here, we removed the dispatcher node. We move its functions on the controller node. We have multiple active controllers. Each controller connect to a subset of the disks. Okay. Here we see a virtual NVMe device allocate the logical disks on the different disk nodes, and then the virtual NVMe device has multiple active controllers. Each controller connect to a subset of these logical disks. And the active controller aggregate the logical disks to a lag, and they export their lag to all other controller nodes. So then each controller node can create a read zero from the local their local lags and all the remote lags. So all the read serial are the same, are exactly the same device. They have the exactly same data. The host can access any of the read serial, and they will forward the traffic to the correct active controller internally. And all the connection between the active controllers and the disk nodes are also use NVMe off. And it's possible to use different NVMe off configurations for this connection. For example, for the connection between host and the controller node, we may use TCP NVMe off for then the storage cluster and your computing cluster may have less dependency with each other. But for the controller node and disk node internally, they may use RDMA. So that means in your in your storage cluster internally, it can have a very good, a better performance. Now we add the standby controller back. So a host may connect to multiple controllers. Some of them are active controllers, and some of them are standby controllers. So the host will only deliver traffic to the active controllers. And if one controller node fails, we will move the active controller to a new, we will promote a standby controller to active controller. Then the host will get the state update from the NVMe protocol, and it will know it should deliver traffic to the new active controller. Okay, here we mentioned we aggregate we create logic disks from the disk node and aggregate them to a lag. And here let's see internal structure of the lag. It connects to the logical disks from the disk node, and we can create a read devices for the data redundancy. Here I use read one as example because it is the simplest one. And then we can create multiple read one devices, and then create the device mapper has a sync-provision module. We can, for the part of the read one devices, we use them as the sync-provision metadata disk, and others we use them as a data disk. Then we can create a sync-provision pool and then create a sync device and export the sync device to the host. So in this case, a sync pool is dedicated for a single virtual NVMe device. It's for that virtual device and all its snapshots. So for different virtual NVMe devices, they will have a different sync pool. The different virtual device doesn't share the same sync pool. So if in the, let's return back to the first I mentioned is it provides a larger granularity sync provision, typically 1 gigabyte to 100 gigabyte. That means because each simple is for a single NVMe virtual NVMe device, we count the granularity should be larger. For a single device, we may allocate 1G, 10G to it. If it needs more disks, we will allocate more disk from new disk node and provide it to that simple. So it's not typically, it's different from some other softwares like Ceph. For Ceph, maybe you can use 4 megabytes for the extend maybe 4 megabytes. So in this product, we should extend it in a larger size because because we don't want to create too many logical disks. They will consume too much resources. So typically, for one leg, we may have several or maybe tens, hundreds logical disks, but should no more. Here is from the host view of the architecture. The host just connect to the different controllers, and some of them are active, some of them are standby. The host deliver traffic to different active controllers. That's all about how we make the data plan work. And the data plan code are just all the exists features in the Linux kernel. So for the data plan, when we build this cluster for the controller node and the disk node, we just configure the Linux kernel to create these active controllers and logical disks and standby controllers. We just create some device mapper devices on them and export them over NVMe off. And the task of this project is building a control plan for it. We want to accept an APIs such as create a volume, export it to a host, and make other things like create a snapshot for it. Typically, it could be used as a Kubernetes customer volume or the CSI driver, or maybe the OpenStack Ceph backend storage. So here is how we build such a control plan. We store all the states in the etcd, and we have API servers. They accept API and store the desired states to the etcd, and we have multiple workers. Each worker will control a subset of the controller node and the disk node. They read data from the etcd and sync up the cluster configuration to the controller node and the disk node. In each controller node and disk node, we have an agent run on it. The agent will communicate with the worker. It will read data. The data should be something like which what kind of device mapper device we should create, and which disk node we should connect to, and we should export it to which host, and then configure the Linux kernel to create the logic device and export the devices over the NVMe. All these agent and worker and API server should be stateless. All the data are stored in the etcd. We can use the STM, the software transactional memory, to control concurrency. That is supported by the etcd. The STM is a client-side transaction. So for either the worker or the API server, when it accepts a request, it will update the etcd. And then if there is no conflict, so different API server could update them at the same time. If there is a potential conflict, the etcd could detect it and report an error to one of the API servers. Then the API server will know it and then retry all the transaction. This is a database technical and already exists. So we can just rely on this for concurrency. Okay, the above one are also about the architecture and the control plan. Here I want to explain some operations the cluster should support. Besides the basic operations like create, delete, or export volumes, we need some, as a distributed cluster, we need additional operations. For example, create snapshot and maybe clone the disk to a new one, or perform a failover, or maybe we want to take one disk offline forever. Before that, we should move all the data from this disk to a new disk, and we should do it transparently. Here I will explain how we do that, do all these things from using the device mapper. First is the snapshot. It's quite simple. We have multiple active controllers. We just suspend the devices on all the active controllers, then issue a supervision snapshot on all these legs. And then after we do that, we resume all these devices. So it's the snapshot. And next one, extend. When a virtual device has more snapshots and they will occupy the more disk occupied more disks. So for example, we want to create a 100 gigabyte disks. Maybe at first we only allocate 10 gigabytes. If there is if the user already writes maybe 9 gigabytes, we need to allocate another 10 gigabytes to these disks. So in this case, we just allocate new logical disks from the new disk nodes, export them to the controller node, and the controller node will suspend the simple, extend it, just follow the just follow the thing provision command the Linux kernel provided to extend it, then resume it. Then we can do it at runtime. That's the extend. And then a very complex one is the failover. For one disk, if a controller node failed, we will choose a standby controller, change its status, we can use the ANA group defined in the NVMe spec. First, we change its states from inaccessible to change, and then run lots of actions to promote the standby controller to the active controller. We just let it connect to the legs and also connect to the remote legs and build the read zero device. When it's ready, we will change the ANA group states from change to optimize. Then it is fully available. So for the ANA group, we mentioned 3 states: inaccessible, change, and optimized. All of them are terms defined in NVMe spec. Typically, I/O timeout should be more than 1 second. For example, 10 seconds. So if the host issue an I/O to a controller, it will wait for 10 seconds until, and then it will see if no response, the host will believe the I/O fails. But when we change the status, when we change the multipath status from inaccessible to change, the host will try to send I/O to this controller and set a shorter timeout. For example, if the timeout is 10 seconds, the host may set the timeout to 1 second and repeat 10 times. So in this case, when our failover finished, the host could run the issues I/O successfully quicker. That's the suggestion of NVMe spec, but the NVMe doesn't define the exactly timeout of the change state. So it depends on the host. And here is the clone. When we may want to clone a virtual device to a new one. So when we clone, we have a source device and a destination device. In this graph, I only show the destination device. The source device is just on the right, the arrow on the right side. So for the source device, we can just create a snapshot on the source device and export that snapshot to the destination device. A virtual NVMe device may have a multiple active controller, but before the clone finish, we should only choose a single active controller. All other active controllers are in the inaccessible state, so the host will only issue requests to a single active controller, and in that active controller, it could do the clone task. Clone is also a device mapper target. When we create a clone virtual device, we could provide a SRC source device and a destination device. It will, then the device mapper clone target will read data from source and write to the destination. At the same time, it could handle IOs. So we can run the clone at runtime. After we clone the device, it could be read and write immediately and copy the data at runtime. All of them rely on the device mapper. And I think the last one is the move data. If we want to offline a disk node, we should move the data to a new disk. If we have a read 1 or read 5 disk, for simple, we can just remove the disk and add a new disk and rebuild the read. But we should do that in the move data scenario because the user do not want to use any read level. For example, the user want to create an HDFS. The HDFS may already have 3 replicas, so the user just don't want any redundancy on the disk level. So we shouldn't assume there are data redundancy on the disk node on a virtual NVMe device. So here when we want to move the data, we also rely on the clone target of the device mapper. Similar as the clone a whole virtual NVMe device. In this case, we just create a clone target between the logical disk of the old disk node and the new disk node. Then the new data will be written to the new disk node. And at the same time, the clone target will copy data from the old disk node to the new disk node. After all the clone task done, we could remove the clone, and then we can offline the old disk node. That's all the operations I want to show. And the next one is a performance test I did. I didn't finish all the control plan code yet, but as the data plan are just the Linux kernel, so I created several batch scripts. Just build the data login to each disk node and controller node, run the batch script to build the virtual disks. Then I can test its performance. The control plan will just replace the batch script to create these functions according to a user API. So here, the first column is the row disk. For each row disk, I have it's about 200 kilo IOPS. That's a NVMe disk. And then we create next one, I create one controller with four legs. 4 legs means we have 4 row disks, and 2 of them, I create a read 1 on 2 of them. In this case, we can have 400K IOPS, and then I continue to increase the controllers and increase the legs. Finally, when I use 8 controllers and 32 legs, I can have more than 2 million IOPS. When I test the performance, if I keep adding more add more pressures to the system, I can get even higher IOPS, but the latency will be very bad. So when I run this test, I try to keep the average latency less than 1 millisecond and the P99 latency less than 2 milliseconds. So then it will make sure it is usable. Okay, and the last one is the future plan of this project. Further finish all the API functions I mentioned, and then I will implement a CSI driver for it. Then it will be usable as a customer storage for Kubernetes. And another plan is using the centralized discover controller to discover the controller node. This is required because, for example, we want to take one controller node offline. The host we may assign a controller to a new controller node. The host should have a way to know it. Right now, if without the CDC, the host should only run something like a discrete API to know the new disk node. But if we have a CDC, the host will know it automatically. Okay, finished. Any question? Okay, no, I think that's all. Thank you.